All right, so as a reminder, when we write conversion factors for things, we first of all need, in order to do this, we need the equality, right? Because we saw in class the last time that an equality can be used to generate two conversion factors always. So if we're looking to see the conversion factors we can get from liters and milliliters, we need to know the relationship between them. So this is a metric relationship, and eventually you should know that 1 liter is equal to 1,000 milliliters. All right, so this is our equality that we have. One thing is equal to another thing. And then this can be used to generate our two conversion factors, which is simply putting one over the other. So that's one conversion factor. Make sure to keep track of your units. And then the other one is just simply taking that first one and flipping it and put milliliters over liters on the bottom. So within a measuring system, we can have these equalities, whether it's the metric system or the US system or any other type of measuring system. We can generate, or we can know these equalities that we can then use to generate two conversion factors. Now we can also get conversion factors from within a problem itself that you're posed with. So for instance, let's say that you're told that a car travels at 85 kilometers per hour. Okay, this is the same thing as saying 85 kilometers per 1 hour. Right, and if you take a close look at that, that looks just like one of the conversion factors we saw previously. We can take this and we can do the same thing that we did to a conversion factor. We can flip it to get the other one. So as you're doing these, keep in mind that you don't just want to use the numbers, you also want to keep track of the units, because the units are really what are we going to use to guide us along the way. Right, so 85 kilometers over hour is the same thing as 85 kilometers per hour. We can flip that to get 1 hour for every 85 kilometers. So those are our two conversion factors from that one. Similarly, if we're told that one tablet contains 500 milligrams of vitamin C, we can say that one tablet is equal to 500 milligrams of vitamin C. That's an equality, and then we get our two conversion factors. One tablet over 500 milligrams of vitamin C, or we just flip that 500 milligrams of vitamin C for every one tablet. We can also get conversion factors from percentages. Right, so for instance, if we're told that a person has 18% body fat by mass, well, we looked at percentages before in the previous chapter, and we said percentages always mean out of 100. So if we're dealing with body mass and we're told that the person has 18% body fat by mass, then that's saying that it's 18 out of 100. Right, well, now your challenge is to decide, well, what is the unit of mass that we're going to use? And in this case, we can just choose any unit that we want, because the ratio is always going to be 18 over 100 based on that percentage. So we can say, for instance, 18 grams of fat per 100 grams of the person. Right, so that's 18 over 100. That is a conversion factor. We can flip it. So if we have 100 grams of that person, whatever that person is, out of that 100, we have 18 grams of fat. So to generate the conversion factors, really, they're not that difficult as long as you have either the equality or you're given that information from the problem itself, and you can just simply flip your initial relationship to get your other conversion factor. All right, and then one more. We're told here that Keflex is an antibiotic used for respiratory and air infections, is available in 250 milligram capsules. All right, so in this case, we have our antibiotic medication that's given to us. So we can say then that 1 capsule is equal to 250 milligrams of our Keflex. Right, that's an equality. And then we have our 2 conversion factors, 1 capsule containing 250 milligrams of the Keflex, and then we just simply flip that on its head. All right, so again, as I'm going through this, hopefully what you're seeing is that I'm putting not just the numbers in, but also the units. All right, let's take a look at another example. We'll choose example C here. We're told that 1 gallon of gas is $2.40, a little bit on the expensive side. But we can take that and we can express it first of all as an equality. So we can say 1 gallon is equal to $2.40. That is our equality. And then just like we did previously, we can put one over the other. So 1 gallon over $2.40, or we just simply flip it, $2.40 over 1 gallon. And that's it. That's how we generate our conversion factors from equalities. So once we have our conversion factors generated, then we can go ahead and start using them to solve problems, right? So we're going to take a look here at problem solving using unit conversions, and this involves the use of what we learned in the previous section of all of these conversion factors. And when it comes to problem solving in general, really what you want to be aware of is how you approach the problem in the first place, right? So how do you analyze it? How do you set it up? How do you make sense of it? Really is probably the best way to approach any problem, whether it's a math problem, a chemistry problem, or any other type of problem. So as you analyze a problem, a couple of things that you want to be aware of. The first of all, you want to think about what are you given. Secondly, you want to think about what you need to get to, or what do you need. To find or calculate. And then thirdly, what are you going to use to get there? Right, and in this case, we're looking at any applicable conversion factors. And then finally, we're going to set up the problem. And at the very end, we always want to check our answer. And then ask ourselves, does it make sense? Right, so not just getting an answer, but thinking about it in a general sense. So let's take a look at a couple examples of how we approach problem solving using dimensional analysis or these conversion factors. So we're told here a person weighs 80.9 kilograms and we need the body mass in grams. All right, so what are we given in this case? Okay, so we're given the person's mass being equal to 80.9 kilograms. We need the mass in grams. So what can we use to get there? Well, we need a relationship between what we're given, kilograms, and what we need, which is grams, right? And that's a metric relationship. And we should know that metric relationship, right? 1 kilogram is equal to 1,000 grams. So that's the tool that we're going to use to help us get from point A to point B. This is an equality, and as we saw, we can generate two conversion factors. We just put one over the other. 1,000 kilograms, 1 kilogram is 1,000 grams, and we just flip it, 1,000 grams for 1 kilogram. All right, so those are the two things that we could possibly use to get from kilograms to grams. Now, the next thing that we're going to do is take a look and see, well, which of those two are we going to use? And what's going to drive our decision are the units. So I mentioned previously that when you set up these conversion factors, you don't just put the number in, you also put the unit, because a unit are going to be your automatic check along the way. All right, so we're going to start with what's given. You always start with what's provided, and that's the 80.9 kilograms. You put that over 1, and then we're going to choose one of these conversion factors, either the one on the left or the one on the right. Now, if we want to end up with grams as our unit, right, that's the unit that should be on top, because we want the other unit, kilograms, to cancel out. So that then would tell us that we need this conversion factor here that has the grams on top. So we're just going to take that and we're going to insert it. So we have 1,000 grams for every kilogram. And the units here are going to tell us now that the kilograms are going to cancel, and you cancel things when they are on opposite sides of the division sign, and we end up with only grams as the unit on top. So in terms of our units, this setup makes perfect sense. All right, so when we multiply that out, we end up with 80.9 times 1,000. So we have 80, decimal point 1, 2, 3 places. So 80,900 kilograms. Grams as our answer, right? And the answer does make sense. Because we're going from a larger unit to a smaller unit. So our final answer should be bigger than what we started with, right? And in this case, it's bigger by a factor of 1,000. So that's a simple example of how we use the dimensional analysis to solve a one-step problem. Let's take a quick look at another example. So we're told a rattlesnake is 2.44 meters long. How many centimeters long is the rattlesnake? Our rattlesnake is 2.44 meters long. All right, and that's what's given to us. 2.44 meters. And then what we need is to convert that to centimeters. All right, and what we're going to use here is the relationship between meters and centimeters, which again is a metric relationship, and you should know that. So 1 meter is equal to 100 centimeters. All right, so that's our equality. We have our two conversion factors that we could use. We just simply put one over the other. And again, keep track of your units when you do this. So then our setup here, we're going to start with what's given. We have our 2.44 meters. We always put that over 1. And then our units now are going to guide us in terms of which conversion factor are we going to use. Since we want to end up with centimeters as the unit, we're going to choose this conversion factor on the right that has centimeters on top, so that the meters on the bottom can cancel out right here. So we end up now with 2.44 times 100, which would give us 244 centimeters as our final answer. That answer makes sense because we're going from a bigger unit to a smaller unit, so our final answer should be bigger than what we start with. All right, so it does make sense. Now, the other thing that you want to keep in mind is the number of sig figs, right? We learned a lot of rules about sig figs before. So let's take a look at this. Our original number here, right, that was 2.44 centimeters. That's the length of a rattlesnake, so that's measured. All right, and that has 3 sig figs. We're multiplying and dividing, and we're multiplying and dividing by that relationship, which is a metric relationship. And remember, your metric relationships, they all have an unlimited number of sig figs because these are exact relationships. So our conversion factor here is not going to limit how many sig figs we have, which means our original number, the 2.44, is going to. So our final answer here has 3 sig figs, which it should, because we started with 3 sig figs multiplied by an unlimited number of sig figs. So the final answer makes sense on a couple levels. So you always want to keep track of your sig figs as well. So those are 2 examples of where we use one conversion factor in a one-step process to go from one unit to another. We're going to start building some complexity and see now how we can incorporate multiple conversion factors in a problem. So let's take a look at an example of one of these. So let's say now that a virus particle has a diameter of 55 nanometers. And we're asked, what is this in kilometers? All right, and we're going to approach it the same way that we approached the previous problems, which was to organize the information in a way that makes sense. And the first thing was, what are we given? Okay, so we're given the fact that this thing is 55 nanometers in diameter, and we need to convert it to kilometers. So now we have to figure out, well, what are we going to use to get from nanometers to kilometers? Well, at this point, you should probably know, as you're becoming more and more familiar with the metric system, that kilo is a much bigger unit than nano. So if we go from a small unit to a big unit, our final answer should be a lot smaller than what we start with. Now, you may not know how many nanometers there are in a kilometer, but what you should know is how those metric prefixes nano and kilo compare to the base unit of length, in this case, which is meters. So we're going to go through, in this case, the base unit for length, which is meters. So our pathway is going to be something like this. We're going to go from nanometers to meters, and then from meters to kilometer. And you should know now what the relationship is between each of those units. So for instance, you may know that 1 meter is equal to 10 to the 9 nanometers. And then you should know that 1 kilometer is equal to 10 to the 3 or 1,000 meters, right? Those are going to be our conversion factors that we're going to use to get us from nano to kilo. So I'm sorry, those are the equalities. So we can take each equality and turn it into 2 conversion factors. So we have 1 meter over 10 to the 9 nanometers, or we flip it, 10 to the 9 nanometers over 1 meter. And then for the other one, 1 kilometer and meters here. We have 1 kilometer over 10 to the 3 meters. And then we flip it to get the other conversion factor. All right, so once we have our steps or our tools, then we can go ahead and set it up using a little bit of logic and then using our units as the guide. All right, so for example, we're going to start with what's provided, which is the 55 nanometers. I'm going to put it over 1. And the first thing that we're going to use, well, the first thing that we have to do is to get from nano to meters. So if you want to end up with meters as the unit, we're going to choose the conversion factor that has meters on top, which is going to be that one. So we're going to take that, insert it here. So we have 1 meter on top, 10 to the 9 nanometers underneath. So the nanometers can cancel, and we end up with meters as our unit. All right, so that gets us to the middle here. We're halfway home. The next step would be to convert our meters into kilometers. Since we want to end up with kilometers, we're going to choose the conversion factor that has kilometers on top, which is that one. So for every kilometer, we have 10 to the 3 meters. So our meters now are going to cancel out, and we only end up with 1 unit, kilometers, which is what we needed. So in terms of our units, our setup here makes perfect sense. All that's left to do is to evaluate this entire thing using our calculator, which may seem simple enough, but you need to be familiar with how you enter those numbers in your calculator. And what we end up with after we plug that into our calculator is 5.5 times 10 to the negative 11 kilometers, right? Expressed properly in scientific notation, and also to the right number of Sig Figs. All right, so our final answer here does make sense on a couple levels. First of all, the unit, right? We followed the units through our conversion factors, and kilometers was the only unit left. Secondly, if we look at the Sig Figs, we started off with 55 nanometers, which has 2 Sig Figs. That's a measured number. Our metric conversions are all exact, so they do not affect the number of Sig Figs. So our answer then can only have 2 Sig Figs. And that's expressed in our coefficient. And then secondly, we talked about the fact that when we go from a small unit, nanometers, to a bigger unit, kilometers, our final answer should be a lot smaller, right? And 10 to the negative 11 is really, really, really small. So this final answer here does make sense. And you want to go through those steps when you're posed with any calculation problem or any problem in general. You want to organize it, figure out what you're given, what do you need, and then what are you going to use to get there. So if we take a look at the next question, we're asked how many minutes are in 1.6 days. All right, so we're given days, and we need minutes. I'm going to abbreviate minute as mins for right now. So you may not know how many minutes there are in a day, but you may know how many hours there are in a day, and you may know how many minutes there are in an hour. All right, so we take that big step and we break it down into 2 bite-sized pieces. So for every day, there are 24 hours. Okay, that's one equality. And then we have our 2 conversion factors we can use. 1 day for 24 hours. Or we flip it, 24 hours for every day. And then hours and minutes relationship, well, for every hour, there are 60 minutes. Right, and we have our 2 conversion factors here as well. 1 hour over 60 minutes. Or we just flip it, 60 minutes for every hour. Right, so keep in mind that both of these equalities and their respective conversion factors, these are all exact. Okay, so they're not going to limit how many Sig Figs we have in our answer. So we have our we organize our information, what we're given, what do we need, and in this case, what we're going to use to get there is to go through hours as our intermediate step. So when we set this up, we set up and we start with what's given, 1.6 days. Put it over 1. Our first conversion factor has to get us to hours, so we're going to choose the one that has hours on top. So 24 hours in 1 day. So day can cancel. And then our second step here is going to get us to minutes, so we need minutes on top. So 60 minutes for every 1 hour, and hours can cancel. So we end up with minutes as our only unit, which makes sense. That's what we needed. And all we have to do is to evaluate this. So this is going to give us 2,304 minutes if you stick that into your calculator. All right, and we said at the beginning here that our time conversions, these are all exact. So they're not going to limit how many sig figs we have, but our original number is, and this has 2 sig figs. So we need to round this to 2 significant figures. So that'll be 2,300 minutes as your final answer. And it does make sense, right? We're going from days, which is a big unit, to minutes, which is a much smaller unit. So our final answer should be a bigger value than what we started with. So now let's take a look at a couple other examples of how we can use conversion factors to help us solve problems. And in this case, we're told that if your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7.5 kilometers? All right, so there's a lot going on in this question, so let's organize the information. All right, so we're told that the pace or the speed is 65 meters per minute, right? And if you recall from a few minutes ago, we said that these types of relationships are actual conversion factors as well, right? 65 meters per minute, and we can flip that. Minutes per 65 meters, right? So per means over 1. We can put that 1 in there to make sure that we don't get confused. So that speed or that pace that's given can actually be used as one of 2 conversion factors. We're also given the distance that's walked. So the distance here is 7.5 kilometers, right? So you'll see that the unit here is in kilometers, but our speed was given in meters. So it would make sense, if you have to do this problem, that you get everything to the same unit, right? So we may want to convert at some point our kilometers into meters. And what we need here, is we need our minutes. As our final answer. All right, so let's start with what's provided, which was the 7.5 kilometers. So we have 7.5 kilometers. Now, in order to use our pace or our speed, we said that we would need to convert our kilometers into meters, right? So 1 kilometer equals 1,000 meters. That's an equality. We can turn that into a conversion factor and stick it in right here. If you want to end up with meters, we're going to put that on top. So 1,000 meters for every kilometer. Kilometers cancel. And now we can go ahead and use our pace that was given to us, right? And we had 2 conversion factors that we generated, And remember, we wanted to end up with minutes as our unit. So we're going to choose the conversion factor that has minutes on top, which is that one. So 1 minute over 65 meters. The meters are going to cancel out. And we end up with minutes as our unit. That makes sense. What we have to do now is to evaluate. And when we evaluate this, all right, we end up with 115.38 ... All right, that's our calculator answer. And we need to make a little bit more sense of that in terms of sig figs. All right, so we have here our 7.5 that has 2 sig figs. Our metric conversion is exact, so that's an unlimited number of sig figs. Our pace here, our speed, has 2 significant figures in it as well. So our final answer needs to be rounded to 2 sig figs. All right, and then that would be, we go to the second one over here. The next digit is 5 or above, so we add 1. This ends up being 120 minutes as our final answer. Okay, so in some cases, we're going to find that, yes, we just have one unit to convert, and we can use our conversion factor to do that. In some cases, we're going to see we have multiple units that we have to convert simultaneously. It may seem, ultra challenging, but really we can use the same technique that we've used before, and we can actually set up our conversion factors for both of those units at the same time. So let's take a look at how we can do this. All right, so we're told here fingernails grow at a measured rate of 2.5 centimeters per year. And we're asked, what is this rate in kilometers per hour? All right, so let's make a little bit of sense of this and organize the information. So we're given our rate or speed of 2.5 centimeters per year. All right, that's what that means. And we need to convert that to kilometers per hour. All right, so we actually have 2 conversions to do. We need to do a distance conversion, centimeters to kilometers, and we also need a time conversion, years into hours. All right, so you can convert each of those individually and then divide them at the end, which is perfectly okay, or you can do them simultaneously using the dimensional analysis technique that we've used previously. All right, so let's take a look at how we can do that. If we want to go from centimeters to kilometers, right, we may not know how many centimeters there are in a kilometer, but we can actually go through meters, which is the base unit, and then we can go from meters to kilometers, right? Just like we did in one of the previous examples. Similarly, we may not know how many hours there are in a year, but we can go from years to days, and then from days into hours, right? So we can break both of these down into a couple chunks or a couple bite-sized pieces. So let's figure out, well, let's write down what the things that we're going to use are. So our first one here is our distance conversion. So we have 1 meter is 100 centimeters, right? That's our equality that we can use over here. And then from meters to kilometers, we know that 1 kilometer is equal to 1,000 meters. That's our second equality that we can use to get from meters to kilometers. For the time conversion, all right, so there's 365 days in 1 year. We can use that to convert years into days. And then from days into hours, well, we know that for every day there are 24 hours. So we have all the tools now, all the equalities that we can possibly use to help us solve this problem. Now we can go ahead and set it up. And again here, our units are going to be our best friend. as we go through this process. So let's set it up. We're going to start with what's provided. Right, you always start with what's given, which is the 2.5 centimeters per year. So keep track of the units. So it doesn't really matter now which unit you want to convert first. Do you want to do the centimeters to kilometers first, or do you want to do the years to hours first? It doesn't really matter. You can do them both in any order. So let's do the distance first. So we want to go from, first of all, from centimeters into meters. We're going to use this here equality as our conversion factor. If we want to end up with meters, I'm going to put meters on top. For every meter, there's 100 centimeters. Centimeters cancel. And then my second conversion would be from meters into kilometers. I'm going to use this one here as my equality, and I'm going to insert that as my conversion factor. If I want to end up with kilometers, that goes on top. 1 kilometer, there's 1,000 meters. So meters cancel out. So up to this point, after these two conversions, the units that I have are kilometers per year. All right, kilometer is the only unit left on top. Year is the only unit left on the bottom. So I'm halfway there. I needed kilometers per hour. So now I can go ahead and do my year to hour conversion, and I can do it right here. So I'm going to go from days, I'm going to go from year into days first of all. I'm going to use this here as this equality as my conversion factor. So I want to go from year to days. So I want years to cancel. I'm going to put year on top. 1 year is 365 days, because the year now can cancel here all the way down at the very beginning. Right? You can cancel things over long distances as long as they are on opposite sides of that division sign. So I'm at days. My final step is to get from days to hours. I'm going to use this as my conversion factor. If I want days to cancel, the day goes on top, and then 24 hours underneath. So days cancels out. So in terms of my unit, the units that I'm left with on top in the numerator, kilometers, and on the denominator on the bottom, the only unit left here is hours. So in terms of the units now, my setup does make sense. All I have to do is to evaluate this using my calculator. So when I plug that into my calculator, I end up with 2.853 dot. The numbers go on for a long time, times 10 to the negative 9, and that's kilometers per hour, right? So that's my calculator answer. We need to round that to the correct number of Sig Figs. So let's see what we have. Our rate here has 2 Sig Figs that we started with, and then all of these other conversions, we can think that those are going to be our exact relationships, right? Our metric ones are always exact, and then we're going to assume here that our time conversions are exact as well. So we need to round our final answer now to 2 Sig Figs. So that'll give us 2.9 times 10 to the negative 9 kilometers per hour. Okay, and that, as you can probably note, is a really small or really slow speed or slow pace. And it should be, right? You're looking at the rate at which fingernails grow, and they don't grow very fast. So the number here makes sense. The units make sense based on our dimensional analysis. Our Sig Figs make sense. And that's how you would approach a problem that has a couple units that you have to convert simultaneously.